Hello, in this lecture we will find out the length of line segment AB on chord AB. We have here a semicircle. Inside this semicircle we have three circles. Those two small circles are identical, and in the middle we have the circle that is tangent to the semicircle at this point O, and point O is also the center of this semicircle, and point C is the center of this circle, of this middle circle, and we know that PQ equals to 8 units. PQ, it is actually the diameter of the semicircle, and the diameter of any circle is twice as large as the radius, so 8 equals to 2 times the radius of the semicircle. Therefore, the radius of the semicircle equals to 4 units. That is to say, PO, that is the radius of the semicircle, equals to 4 units, and OQ also, that is the radius of the semicircle, will be also equal to 4 units. Okay, and OX is also the radius of the semicircle, therefore it equals to 4 units, but OX, it is also the diameter of this middle circle, and the diameter of this any circle is twice as large as the radius. So if the diameter of the middle circle equals to 4 units, then the radius of this middle circle equals to half of 4, that is to say it equals to 2 units. That is to say the radius CX of the middle circle equals to 2 units, and OC, that is also the radius of this middle circle, equals to 2 units. And we have those two centers. We define the center of this small circle as point M. So we join together points P, M and C by a straight line. So MC is the distance between the centers of those two circles, and the distance of two circles that have a large point between them, an external large point between them, is equal to the sum of the length of their radiuses. If we define the radius of this small circle as R, and we know that the radius of the middle circle equals to 2 units, then the distance MC equals to 2 plus R. Okay, so MC equals to 2 plus R. Then we know that PQ is tangent to this small circle. At this point, we define the touching point between the tangent PQ and the small circle is point N. Point N is the point of tangency of tangent PQ with this small circle. We will join together points M and N by a straight line. MN is the radius of this small circle, that is to say it equals to R, because it starts from the center of the small circle, that is to say from point M, and ends at point N, that is a point on the small circle itself. Therefore MN is the radius of this small circle, and this radius is drawn to the point of tangency, that is to say it is drawn to point N, that is the point of tangency of tangent PQ with this small circle. Therefore the tangent PQ will be perpendicular to this radius, that is to say this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we have the radius OC of the middle circle that equals to 2 units, that is drawn to the point of tangency, that is to say it is drawn to point O, that is the point of tangency of tangent PQ with this middle circle. Therefore, the radius PQ is perpendicular to the tangent PQ is perpendicular to this radius OC that is drawn to the point of tangency, that is to say it is drawn to point O, that is the point of tangency. Therefore, the tangent PQ is perpendicular to this radius, that is to say this angle is a right angle, it equals to 90 degrees, and this angle it is also a right angle that equals to 90 degrees. So we have here two right angles. Then we will draw perpendicular from point M to OC. So actually this angle will be equal to 90 degrees, and this angle also will be equal to 90 degrees. We will define the touching point between the perpendicular and the OC as point D, and actually it is given us in the question that AB is perpendicular to PQ, and because of the fact that AB is perpendicular to PQ, then those two angles are corresponding angles that are located between the parallel lines AB and PQ. Therefore, they are equal to each other, and if this angle is a right angle, then this angle will be also a right angle, that is to say it will be equal to 90 degrees. Okay, so I will draw again the quadrilateral NOMD and the right triangle CMD in another page in order to clarify the issue, and it will be more clear and bigger. So here we have the perpendicular NMDO. The perpendicular NMDO, it is actually, it has three right angles. Again, the perpendicular MNO and OD has three right angles. we will define this point as point E. And we will define the touching point between the two circles as point Y. So I actually draw the perpendicular MNO DO again, and also the right triangle MCD and the right triangle YEC. Actually, this perpendicular, this quadrilateral MNDO has four right angles, has three right angles, 1, 2, 3. We write it down. Perpendicular quadrilateral MNOD has three right angles, and the sum of those three right angles, it is actually 90 times 3 is equals to 270 degrees, plus the size of this angle that I will define as angle X. So the sum of those four angles inside quadrilateral MNOD must be equal to 360 degrees. I repeat again. The sum of the angles in any quadrilateral is equal to 360 degrees. That is to say, the sum of three angles, that is 270 degrees, plus the size of the fourth angle must be equal in total to 360 degrees. Because of the rule that the sum of the angles in any quadrilateral equals to 360 degrees. Here we will subtract 270 degrees from this equality, and we will get that the size of angle X, it is actually equals to 360 degrees minus 270 degrees, it equals to 90 degrees. So we actually found out that this angle is a right angle, that is to say, it equals to 90 degrees. So actually, quadrilateral MNOD has four right angles. Okay, I will repeat again. Quadrilateral MNOD has four right angles. And any quadrilateral that has four right angles must be at least a rectangle, if not a square. So I write it down. Rule number 1 states that any quadrilateral that has four right angles must be at least a rectangle, if not a square. I will repeat on rule number 1. According to rule number 1, any quadrilateral that has 4 right angles must be at least a rectangle. So therefore, in any rectangle, the opposite sides of a rectangle are equal to each other. According to rule number 2, the opposite sides of a rectangle are equal to each other. The opposite sides of a rectangle are equal to each other. I will repeat on rule number 2 again. According to rule number 2, the opposite sides of a rectangle are equal to each other. Therefore, according to rule number 2, side MN of rectangle MNOP equals to side OD. MN equals to OD. MN equals to OD. According to rule number 2, that the opposite sides of a rectangle are equal to each other. MN equals to OD. The opposite sides MN and OD are equal to each other according to rule number 2. I will repeat again. MN equals to OD according to rule number 2, that the opposite sides of a rectangle are equal to each other. But we know that MN equals to R. MN equals to R. We found out that MN equals to R, so from this equality we will conclude that OD also equals to R. OD also equals to R. OD also equals to R, that is the radius of the small circle. OD equals to R, the radius of the small circle. And we know that CO is the radius of the middle circle, as you can see here. CO, it is the radius of the small circle, and the radius of the small circle equals to 2 units. Okay, the radius of the small circle CO equals to 2 units. So actually we can write here that CO, that is the radius of the small circle, equals to 2 units. And we know that DO is equals to R, the radius of the small circle. And in total, we will get that CD, what is the value of CD? CD, you can see from the drawing that side CD equals to CO equals to CO minus DO. Again, CO minus DO equals to CD. Okay, CO minus DO equals to CD. That is to say, CD equals to CO, that is 2 units, minus DO, that is the radius, that is to say, CD equals to 2 minus R. Okay, so I will write it down that CO equals to CD equals to CO minus DO. CD equals to CO minus DO, and CO equals to 2 units, and DO is the radius of the small circle. So in total we got that CD equals to 2 minus R. CD equals to 2 minus R. And what is the value of MC? What is the value of MC? So you can see from this drawing the value of MC. MC, it is actually the distance between the two centers of the small circle and the middle circle. And the distance between the two circles, it is the sum of their radiuses. That is to say, it equals to R, that is the radius of the small circle, plus 2, that is the radius of the middle circle. So in total, MC equals to R plus 2. So we can write here that MC equals to R plus 2. MC equals to R plus 2. MC equals to R plus 2. As I already mentioned, when you have an internal lunge between external lunge between two circles, then the distance between their centers equals to the sum of the length of their radiuses. And the length of the radius of the small circle is R, and the length of the radius of the middle circle is 2. Therefore, the distance between their centers, that is to say, MC equals to R plus 2. Therefore, MC equals to R plus 2. And CD equals to 2 minus R. So we will focus on the right triangle CDM. So on the right triangle CDM, according to the Pythagoras theorem, on the right triangle CDM, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars in any right triangle, and especially in the right triangle CDM, the square of the hypotenuse is MC squared, because the hypotenuse is MC, and the square of the hypotenuse is MC squared, and it will be equal to the sum of the squares of the perpendiculars. The sum of the squares of the perpendiculars, it is actually CD squared plus MD squared. So I repeat again. According to the Pythagoras theorem, in the right triangle CDM, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say MC square equals to CD square plus MD square. Okay? But what is the value of MC? We have already found out that the value of MC, it is actually equals to R plus 2. MC equals to R plus 2. Therefore, MC square will be equal to R plus 2 square. And it equals to CD square. CD equals to 2 minus R. So CD square will be equal to 2 minus R square plus MD square. So I'll repeat again. So MC square equals to CD square plus MD square. MC equals to R plus 2. So MC square will be equal to R plus 2 square. And it equals to CD square. CD equals to 2 minus R. So CD square will be equal to 2 minus R square plus MD square. MD square is MD square. We will leave it as it is. Here we will open the brackets of equation number 1 on both sides of equation number 1. This equation, and we will get that R plus 2 square, R plus 2 square, it is actually equal to R square plus 4 plus 4R, and it equals to 2 minus R square. 2 minus R square equals to 2 square is 4 plus R square minus 4R plus MD square. Okay? So here we have R square on both sides of equation number 1, so R square will get cancelled. And we also have 4 on both sides of equation number 1, so 4 will be also cancelled. And what is left after we cancel those two expressions, what is left, it is actually 4R equals to minus 4R plus MD square. So here we will add 4R to this equation, equation number 1, and we will get that 4R plus 4R is 8R. 8R equals to MD square. 8R equals to MD square. So here we will take a root out of equation number 1, and we will get that MD equals to the square root of 8R. MD, according to equation number 1, MD equals to the square root of 8R. So here we got that after we took a root out of this equation, equation number 1, we found out that MD equals to the square root of 8r. So here we know that 8 is 4 times 2, so we will substitute 8 by 4 times 2, and we will get that according to equation number 1, MD equals to the square root of 4 times 2 times r. We know that the square root of 4 is 2, so we'll write it down. We'll get that MD equals to the square root of 4 is 2. 2 times, inside the root we will have 2r. So in total we found out that the value of MD, it is actually equal to 2 times, we found out that the value of MD equals to 2 times the square root of 2r. So we can write here that MD equals to 2 times the square root of 2r. And because of the fact that the opposite sides of any rectangle are equal to each other, it means that MD equals to MD. The two opposite sides, MD, will be equal to MD. MD is equals to ND. According to the rule that the opposite sides of a rectangle are equal to each other, therefore MD equals to ND. But we have already found out that MD equals to 2 times square root of 2r. We have already found out that MD equals to 2 times the square root of 2r. Okay, so from this equality, we will conclude that ND also equals to 2 times square root of 2r. ND also equals to 2 times square root of 2r. So we can write here that ND, this, it is actually, okay, it is NO, okay, it is NO, NO actually equals to 2 times square root of 2r. It is not D but O, so NO equals to 2 times square root of 2r. Okay, so in the next step we will connect together points M and O by a straight line. Okay, we connect together points M and O by a straight line, and we will also connect here points M and O by a straight line. And then we will connect together points M and A by a straight line. As you can see from the drawing, MA is the radius of this small circle because of the fact that line segment MA starts from the center of the small circle, that is to say from point M, and ends at point A, that is the point on the small circle itself. Therefore AM or MA is the radius of the small circle, that is to say it equals to R. And we also know that OA is the radius of the semicircle because of the fact that it starts from point O, that is the center of the semicircle and ends at point A, that is a point on the semicircle itself. Therefore, OA is the radius of the semicircle, that is to say, it equals to 4 units. So OA equals to 4 units. OA equals to 4 units as the radius of the semicircle, and MA equals to R, it is the radius of the small circle. And what is the value of OM? The value of OM, as you can see from this drawing, OM equals to OA minus AM. I repeat again, OM, this line segment OM, equals to OA minus AM. It equals to OA minus AM. Again, MO or OM, this line segment OM equals to OA minus AM. So I write it down. OM equals to OA, that is the radius of the semicircle, minus MA, that is the radius of the small circle. OM equals to OA minus MA. So OM equals to OA, that is the radius of the semicircle, that is to say, it equals to 4, minus MA, that is the radius of the small circle, that is to say, it equals to R. So in total we got that OM equals to 4 minus R. So here OM equals to 4 minus R. So we can write here also that OM, the hypotenuse of triangle MNO, equals to 4 minus R. Okay, so in the next step we will focus on the right triangle, triangle MNO. So we will actually focus on this right triangle, triangle MNO. I will paint it in the green color. We will focus on this right triangle, triangle MNO. On this right triangle, triangle MNO, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Okay? So we will focus on the right triangle, triangle MNO. According to the Pythagoras theorem, in the right triangle, triangle MNO, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Okay, on the green right triangle, triangle MNO, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The square of the hypotenuse is MO square. And it equals to the sum of the squares of the perpendiculars. That is to say, it equals to MN square plus NO square. I will repeat again, in the right triangle, triangle MNO, according to the Pythagoras theorem, that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle MNO, it means that MO square equals to MN square plus NO square. But what is the value of MO? The value of MO, as you can see, the value of MO is 4 minus R. So MO square will be equal to 4 minus R square. And it equals to Mn square. Mn equals to R. Therefore, Mn square will be equal to R square plus NO square. NO square. NO equals to 2 times square root of 2R. Therefore, NO square will be equal to 2 times square root of 2R square. Okay, so in total we got that MO equals to 4 minus R, therefore MO square will be equal to 4 minus R square. Mn equals to R, so Mn square will be equal to R square. And NO equals to 2 times square root of 2R, therefore NO square will be equal to 2 times square root, 2 times the square root square. Okay, so here we'll open the brackets on both sides of equation number 2, and we will get that four minus R square, it is actually 16 minus 8R plus R square, and it equals to R square plus, we have the square, we have 2 times the square root of 2R square. 2 times the square root of 2R square, it is actually 8R. So here we actually have R square here we have R square on both sides of equation number 2, so R square will get cancelled. After we cancelled R square, we will add 8R to equation number 2, and we will get that 16 according to equation number 2, 16 equals to 8R plus 8R is 16R. So we actually got that 16 equals to 16R. So here we will divide the equation by 16. We got that 16 equals to 16R. We will divide this equation number 2 by 16, and we will get that R, the radius of the small circle, according to equation number 2, equals to 1 unit. R equals to 1 unit. According to equation number 2, the radius of the small circle equals to 1 unit. So here we can write down that R, the radius, equals to 1. And we know that CD equals to 2 minus R. It means that it equals to 2 minus R is 1. So 2 minus 1 is 1. So CD equals to 1. And OD equals also to 1. And so in the next step, we will prove that the right triangle CEY, this right triangle, is similar to the right triangle CDM. Okay, so actually, I'll repeat again, we'll prove that the right triangle CDM is similar to the right triangle CEY. So I write it down. we prove that the right triangle CDM, this right triangle is similar to the right triangle, triangle CEY, this small right triangle. Again, we will prove that the right triangle CDM and CEY are similar to each other. First of all, we have those two angles, they are right angles, therefore they are equal to each other. So we can write down that angle CEY of triangle CEY is equal to angle CDM, this angle of triangle CDM, and both angles are right angles, that is to say they are equal to 90 degrees. So I will repeat again. Actually, we proved that angle CY equals to angle CDM, and they are both equal to 90 degrees, they are right angles. And we also know that this angle C, it is a common angle because angle C belongs to triangle CEY and angle C also belongs to triangle CDM. So we can write down that angle C equals to angle C is a common angle that belongs to both triangles. Angle C equals to angle C is a common angle that belongs to both triangles. Again, angle C equals to angle C. It is a common angle that belongs to both triangles. And finally, we have those two angles that are also equal to each other. That is to say, angle CYE from triangle CYE, this angle equals to angle CMD, this angle of triangle CMD. So those two angles are equal to each other according to third angle theorem. So I'll write it down. Angle CYE, this angle is equal to angle CMD, this angle, and they are equal to each other according to third angle theorem. They are equal to each other according to third angle theorem. I will repeat again. Angle CYE of triangle CYE equals to angle CMD of triangle CMD, and they are equal to each other according to third angle theorem. So what is third angle theorem? Third angle theorem states that if two angles of one triangle congruent to two angles of another triangle, then those two triangles are similar to each other. Then those two triangles are similar to each other. Okay? Actually, it is a little bit different. The third angle theorem states that if two angles of one triangle congruent to two angles of another triangle, so we have two pairs of angles that congruent on those triangles, then if this is the situation, then the third pair of angles must also congruent. That is to say, if we have two triangles with two pairs of angles that congruent to each other, then the third pair of angles must also congruent. Okay? So here we actually proved that two angles, this is the first pair of angles that congruent in both triangles, and this is the second pair of angles that congruent to each other. It is actually a common angle. Therefore, the third pair of angles, those angles that are the third pair of angles, must also congruent. That is to say, those angles are equal to each other. Or in other words, angle CYE equals to angle CMD according to third angle theorem. Okay, so we actually proved that all three angles of triangle CDM congruent to all three angles of triangle CEY. Therefore, we actually proved that those two triangles are similar to each other according to angle similarity rule. So I will write it down. So, because of the fact that we have three angles of triangle CDM that are congruent to three angles from triangle CEY, therefore triangle CDM is similar. This is the sign of similar to triangle CEY according to angle similarity rule. I will repeat again. Because of the fact that we proved that all three angles of triangle CDM congruent to all three angles of triangle CEY, we proved that those two triangles are similar to each other. That is to say, triangle CDM similar to triangle CEY according to angle similarity rule. So what is angle similarity rule? Angle similarity rule is that if you prove that all three angles of one triangle congruent to all three angles of another triangle, then you actually proved that those two triangles are similar to each other according to angle similarity rule. So from the fact that triangle CDM is similar to triangle CYE, we will conclude that the following equality is true. The equality that states that CE over CY, CE over CY in triangle CY equals to CD over CM in triangle CDM. CD over CM in triangle CDM. I will repeat again. From the fact that triangle CDM is similar to triangle CEY, we will conclude that CE over CY in triangle CEY equals to CD over CM in triangle CDM. Okay, but CE, we have also CE, we have here CE over CY. What is the value of CY? The value of CY, as you can see from the drawing, CY, here CY, as you can see it from the drawing, CY equals to 2 units. CY, it is actually the radius of the middle circle. Therefore, it equals to 2 units. Again, CY is the radius of the middle circle, therefore it equals to 2 units. So Cy equals to 2 units, and all equals to CD. What is the value of CD? The value of CD, you can see it from the drawing, that the value of CD is 2 minus R, and R equals to 1, therefore CD equals to 2 minus R is 1, so 2 minus 1 is 1, so CD equals to 1 over Cm. What is the value of Cm? Cm equals to R plus 2. Cm equals to R plus 2 and R equals to 1. So Cm equals to R, that is 1 plus 2. 1 plus 2 is 3. So in total we found out that Ce according to equation number 3, Ce over 2 equals to 1 over 3. Okay, here we will multiply equation number 3, this equation, by 2, and we will get that Ce equals to 2 over 3 units. We will find out that Ce equals to 2 over 3 units. Ce, according to equation number 3, equals to 2 over 3 units. So we can write here that Ce here equals to 2 over 3 units. It equals to 2 over 3 units. And you can see here, we know that here CD equals to 1 unit. CE equals to 2/3 units. Therefore, DE or ED will be equal to CD minus CE. I repeat again, DE will be equal to CD minus CE. DE equals to CD minus CE. DE equals to CD minus CE, and CD equals to 1 unit, and CE equals to 2 over 3rd. So DE equals to 1 minus 2 over 3rd, that is to say DE equals to 3rd. DE equals to 3rd, or 1 over 3. Okay, I'll repeat again. DE equals to CD minus CE, and CD equals to 1, and CE equals to 2/3. So in total, DE equals to 1 minus 2/3. 1 minus 2/3 is 3rd. That is to say DE equals to 1 over 3rd, or DE equals to 3rd. DE equals to 3rd. So we can write here that DE equals to 3rd. And what is the value of OE? The value of OE, the value of OE equals to R plus DE. OE equals to R plus DE, or OE equals to OD plus DE. Okay, I will repeat again. OE equals to OD plus DE. That is to say OE equals to OD, that is 1, plus DE, that is 3rd. So in total, OE equals to 1 plus 3rd. 1 plus 3rd is 4/3, or OE equals to 4/3. Okay, I'll repeat again. OE equals to OD plus DE, and OD equals to 1 and DE equals to 3rd. So in total, OE equals to 1 plus 3rd, that is to say it equals to 4 over 3rd. OE equals to 4 over 3 units, O equals to 4/3 units. Okay, so in the next step we will connect together points O and B by straight line. We'll connect together points O and B by straight line. We know that OB is the radius of the semicircle, that is to say it equals to 4 units. Okay, OB is the radius of the semicircle, that is to say it equals to 4 units. And what is the size of angle OEB? What is the size of angle OEB? Actually, we know that AB is parallel to PQ. Because of the fact that AB is parallel to PQ, we know that the sum of one-sided angles between parallel lines is equal to 180 degrees. So I will write down rule number 3. Rule number 3 states that the sum of one-sided angles between parallel lines is equal to 180 degrees. The sum of one-sided angles I'll emphasize that AB is parallel to PQ. And we have the rule that the sum of one-sided angles between parallel lines equals to 180 degrees. So I will read rule number 3 again. According to rule number 3, the sum of one-sided angles between parallel lines equals to 180 degrees, and we know that AB is parallel to PQ. We know that AB is parallel to PQ, therefore the sum of those one-sided angles must be equal to 180 degrees. That is to say, here is 90 degrees plus angle OEB, this angle must be equal to 180 degrees. Again, we have the rule that the sum of one-sided angles between parallel lines equals to 180 degrees. And we know that side AB is parallel to side PQ. Therefore, the sum of the those two one-sided angles must be equal to 180 degrees according to rule number 3. That is to say, this angle that equals to 90 degrees plus the size of angle OEB must be equal to 180 degrees according to rule number 3. I will repeat again. We know that AB equals to PQ, therefore according to rule number 3, the sum of those two right angles, 90 degrees plus the size of angle OEB, must be equal to 180 degrees according to rule number 3. Here we will subtract from this equality 90 degrees, and we will get that the size of angle OEB, equals to 180 degrees minus 90 degrees is 90 degrees. We found out that angle OEB equals to 90 degrees. So this angle is a right angle, and because of the fact that angle OEB is a right angle, it equals to 90 degrees, therefore triangle OEB is a right angle, because it has one angle that equals to 90 degrees. So I will copy again this right triangle, triangle OEB. Okay, I will copy it again. So triangle OEB So this triangle OEB is a right triangle because it has one angle that equals to 90 degrees. We have already found out that side OE equals to 4 over 3 units. It equals to 4 over 3 units, and OB, it is the radius of the semicircle, therefore it equals to 4 units. Okay, so we have here a right triangle, and two sides of it are known, and the only thing that is left to do is to find out the size of side EB. And according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, in this triangle OEB, the square of the hypotenuse, it is actually OB square. OB square equals to the sum of the squares of the perpendiculars equals to OE square plus EB square. So according to the Pythagoras theorem, in the right triangle OEB, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, OB square equals to OE square plus EB square. And we know that OB equals to 4 units. OB equals to 4 units. Therefore, OB square will be equal to 16 because it is 4 square. 4 square is 16. 16 equals to OE square. OE equals to 4 over 3. So OE square will be equal to 4 over 3 square plus EB square I'll repeat again. OB equals to 4, so OB square is 4 square. 4 square is 16. OE equals to 4 over 3. Therefore, OE square will be equal to 4 over 3 square. And EB square is EB square. Here, 4 over 3 square is 16 over 9, so I write it down. 16 over 9, 16 equals to 16 over 9 plus EB square here we will subtract 16 over 9 from this equality and we will get that 16 minus 16 over 9 equals to EB square. So here we will multiply 16 by 9 and then we will divide it by 9 in order to have a common factor with 16 over 9. So we will get that 16 times 9 over 9 minus 16 equals to EB square. So here 16 times 9 minus 16 is 16 times 8, so I write it down. We got that according to question number 4, 16 times 8 over 9 equals to EB square. So we got that 16 times 9 over 16 times 8 over 9 equals to EB square. Here we will take a root out of equation number 4 and we will get that EB equals to the square root of 16 times 8 over 9. Okay, we know that 16 is 2 times 8, so we write it down. 2 times 8 times 8 over 9. So EB equals to the square root of 2 times 8 times 8 over 9. The square root of 8 times 8 is 8 and the square root of 9 is 3, so we write it down. So we got that EB equals to 8 over 3 times square root of 2 units. So we found out that EB equals to 8 over 3 times square root of 2 units. Okay, we found out the value of EB. It equals to 8 over 3 times square root of 2 units. But what is so in the next step we will prove that those two right triangles can go into each other. The right triangle OEB, the green triangle, is congruent to the other green triangle OEA. We will prove that those two right triangles in the green color can go into each other. So I will copy it again and we will prove that those two right triangles can go into each other. Okay? So actually we prove that triangle OEA I will repeat again. We will prove that those two right triangles can go into each other. That is to say, triangle OEB is congruent to triangle OEA. So first of all, we know that OB equals to 4 units and OA is also equals to 4 units. So in the right triangles OEB and triangle OEA, those two right triangles, we know that OB of triangle EOB is equal to OA of triangle OEA, and both equals to 4 units. They are the radiuses of the semicircle. And we also know that OE is a common side. OE equals to OE is a common side that belongs to both triangles. O equals to OE as a common side. And actually we proved that those two triangles can go into each other. We actually proved that triangle OEB can go into triangle OEA. Triangle OEB can go into triangle OEA. Okay, those triangle OEB is congruent. This is the sign of congruent to triangle OEA, according to the rule that if you have a hypotenuse and perpendicular, if the hypotenuse and the perpendicular of one triangle of two right triangles congruent, so if the hypotenuse and the perpendicular of two right triangles congruent, or if the hypotenuse and the perpendicular of one right triangle congruent to the hypotenuse and the perpendicular of another right triangle, then the right triangles congruent to each other. So I repeat on the rule again. If the hypotenuse and the perpendicular of one right triangle congruent to the hypotenuse and the perpendicular of another right triangle, then the two right triangles, then the two right triangles congruent to each other. Okay? Again, if the hypotenuse and the perpendicular of one right triangle congruent to the hypotenuse and the perpendicular of another right triangle, then the two right triangles congruent to each other. And we proved that the hypotenuse and the perpendicular of this triangle congruent to the hypotenuse and the perpendicular of this right triangle. Therefore, we proved that those two right triangles congruent to each other according to this rule. So from the fact that those two triangles congruent to each other, we will conclude that AE equals to EB, AE equals to EB, according to the rule that corresponding angles in congruent triangles are equal to each other. AE equals to EB according to the rule that corresponding angles in congruent triangles are equal to each other. Okay? But what is the value of AB? You can see from the drawing that AB equals to AE plus EB. Okay? According to the drawing, AB equals to AE plus EB, but we have already proved that AE equals to EB, so we can substitute AE here by EB. Okay, we'll substitute AE by EB here because AE equals to EB, and we will get that AB equals to EB plus EB. That is to say, AE equals to 2 times EB. And we have already found out that EB equals to 8/3 times square root of 2 units. So in total, we found that AB equals to 2 times 8/3 times square root of 2 units. That is to say, AB equals to 16/3 times square root of 2 units, or in terms of numbers, AB equals to 7.54 units. Okay, I will repeat again. We actually found out that AB equals to 16/3 times square root of 2 units, or in terms of numbers, AB equals to 7.54 units. I'll repeat it again here. we actually found out that AB chord AB, this chord AB equals to either 16/3 times square root of 2 units, or in terms of numbers, this chord AB equals to 7.54 units. Okay, so now I will summarize the lecture. Actually, we wanted to find out the length of chord AB. We have here a semicircle, and inside of this semicircle we have 3 circles inside this semicircle, and we know that the middle circle is tangent to the semicircle at point O, and point O, it is also the center of this semicircle. Okay, and we also know that point C is the center of this middle circle, and those two small circles are identical, and those two circles have an external lunge between them, and the touching point between those two circles is at this point, point Y, and we want to find out the size of chord AB. Okay, so actually I draw again the two, the quadrilateral and the I do again the quadrilateral. So here we have the quadrilateral MN O D, but before that actually we have the tangent PQ is tangent to this small circle at point N, and we have the radius MN that is drawn to the point of tangency, that is to say it is drawn to point N, that is the point of tangency. Therefore the tangent PQ is perpendicular to the radius, that is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we have the tangent PQ that is tangent to this middle circle at point O, and we have the radius CO of the middle circle that is drawn to the point of tangency, that is to say, the radius CO is drawn to point O, that is the point of tangency of tangent PQ with this middle circle. Therefore, the tangent PQ will be perpendicular to this radius OC, that is to say, this angle equals to 90 degrees and this angle also equals to 90 degrees. So we have here inside quadrilateral MN DO two right angles, and we also from point M drew perpendicular to OC or CO. So this angle equals to 90 degrees and this angle also equals to 90 degrees. And here we have, we know that side AB is perpendicular to PQ. It is given us the question. Therefore, those two angles are equal to each other. We know that this angle equals to 90 degrees. Therefore, this angle will be also equal to 90 degrees. Okay, so here we have in quadrilateral MN DO, we have three right angles. 1, 2, 3. Those are three right angles. And we will calculate the size of the fourth angle, and we will define the fourth angle as x. Okay, so I draw again the quadrilateral. We have here three right angles, 1, 2, 3, and we want to find out the value of this angle. So we define it as x, and we know that the sum of the three right angles is 270 degrees, plus the size of the fourth angle that is defined as x must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. That is to say, in quadrilateral MNOB, 270 degrees plus the size of the fourth angle must be equal to 360 degrees. We subtracted 270 degrees from this equality, and we got that the size of angle x equals to 360 degrees minus 270 degrees, it equals to 90 degrees. So we actually found out that all three angles inside quadrilateral MNOD are right angles. And any quadrilateral that has four right angles, it must be at least a rectangle. Okay, any quadrilateral that has four right angles must be at least a rectangle according to rule number 1. Therefore, quadrilateral MNOQ is at MNOD, this quadrilateral is at least a rectangle. And we also have the rule number 2 that states that the opposite sides of a rectangle are equal to each other. Okay, the opposite sides of a rectangle are equal to each other. And we know that MN is the radius of the small circle, that is to say it equals to R. And according to rule number 2, MN equals to OD, because there are two opposite sides in quadrilateral MNOD. So MN equals to OD according to rule number 2. MN equals to OD according to rule number 2. But we already know that MN equals to R. MN equals to R. So from this equality we will conclude that OD also equals to R. OD also equals to R. And what is the size of CD? The size of line segment CD, it is actually CO minus DO. Again, CD equals to CO minus DO. And we know that CO is the radius of the middle circle, that is to say it equals to 2 units. And DO equals to R, that is the radius of the small circle. So in total we got that CO equals to 2 minus R, because it is CO that is 2 minus DO that is R. In total CO equals to 2 minus R, or CD. This CD equals to 2 minus R. So we found out that CD equals to CO minus DO, that is to say it equals to 2 minus R, CD equals to 2 minus R. Okay? And then we focused on the right triangle, triangle CDM. Triangle CDM is a right triangle because this angle equals to 90 degrees according to the Pythagoras theorem. In the right triangle, triangle CDM, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. And the square of the hypotenuse is CM square equals to the sum of the squares of the perpendiculars. That is to say it equals to CD square plus MD square. So in the right triangle, triangle CDM, MC square equals to CD square plus MD square. MC, it is actually the distance between the two centers. The distance of the two centers, between the two centers of the small circle and the middle circle, it is the sum of their radiuses. That is to say it equals to R plus 2. So CM equals to R plus 2. Therefore CM square will be equal to R plus 2 square. And it equals to CD. We already found out that CD equals to 2 minus R. Therefore CD square will be equal to 2 minus R square plus MD square. MD square is left as MD square. Here we open the brackets of this equation, equation number 1, and we got that R plus 2 square equals to R square plus 4R, and it equals to 2 minus R square. 2 minus R square, it is actually 4 plus R square minus 4R plus MD square. Here we have R square on both sides of equation number 1, so we subtracted R square from equation number 1, or R square will be cancelled, and we have 4 on both sides of the equation number 1, so 4 is also cancelled, and in total what is left, after we cancel those expressions, what is left is it is actually 4R equals to 4R plus MD square. So here we added 4R to this equation number 1, and actually 4R plus 4R is 8R, and 8R equals to MD square. And here we take a root out of equation number 1, and we got that MD equals to the square root of 8R. MD equals to the square root of 8R. So here we know that 8 equals to 4 times 2. So we substituted 8 by 4 times 2. And we got that MD equals to the square root of 4 times 2R. And we know that the square root of 4 is 2. So in total we got that MD equals to 2 times square root of 2R. And here we know that, so we got that MD equals to 2 times square root of 2R. MD equals to 2 times square root of 2R. But we know that quadrilateral MNDO is at least a rectangle, and the opposite sides of a rectangle are equal to each other. So MD equals to NO. MD equals to NO, and MD, we know that MD equals to 2 times square root of 2R. So if MD equals to NO and MD equals to 2 times square root of 2R, then ND will be also equal to 2 times square root of 2R. Okay, then we focused the value of OA. The value of OA it is actually 4. It is the radius of the semicircle. The value of MA is R. It is the radius of the small circle. And OM equals to OA minus AM, that is to say OM equals to OA, that is 4, minus AM or MA, that is R. In total, we found out that OM equals to 4 minus R. OM equals to 4 minus R. And we have already found out that ND equals to 2 times square root of 2R, and NM is the radius of the small circle, that is to say it equals to R. So in the green triangle, green right triangle, triangle MND, the square of the, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say MD square equals to MN square plus NO square. We know that MO equals to 4 minus R, so MO square will be equal to 4 minus R square. That equals to NM square. NM equals to R, so NM square equals to R square plus NO square. We know that NO equals to 2 times square root of 2R. So the NO square will be equal to 2 times square root of 2R square. So here we open the brackets in both sides of equation number 2, and we got that 4 minus R square equals to 16 minus 8R plus R square, that equals to R square plus 8R, because 2 times square root of 2 square equals to 8R. So here we have R square in both sides of equation number 2, so R square will get cancelled, and what is left after we cancelled R square? What is left, it is actually, after we cancelled R square, we added 8R to this equation, equation number 2. So here 8R plus 8R is 16R. So 16R equals to 16. We got that 16R equals to 16. We divided this equation, equation number 2, by 16, and we got that the radius of the small circle equals to 1 unit. Then we proved the triangle CDM, the right triangle CDM, is similar to the right triangle, triangle CEY. Why they are similar to each other? Those two right triangles are similar to each other. Why? Because we have two right angles that are equal to each other. That is to say, angle CEY equals to angle CDM, and those both angles are right angles, they are equal to 90 degrees, and therefore they are equal to each other also. And we have this angle, angle C, it is a common angle, it belongs to both triangles. So we can write down that angle C equals to angle C is a common angle that belongs to both triangles. Angle C equals to angle C is a common angle that belongs to both triangles. Then we have those two angles that are equal to each other according to third angle theorem. So what is third angle theorem? According to third angle theorem, if you have two angles of one triangle congruent to two angles of another triangle, then the third pair of angles must also congruent. And we proved already that two angles of those two triangles congruent to each other, therefore the third pair of angles must also congruent according to third angle theorem. That is to say, those two angles are equal to each other. Okay, so we actually proved that all three angles of triangle CDM congruent to all three angles of triangle CEY. Therefore, we proved that those two right triangles congruent to each other according to angle similarity rule. We proved that triangle CDM is congruent, is similar to triangle CEY. This is the sign of similar, so triangle CDM is similar to triangle CEY according to angle similarity rule. And from the fact that triangle CDM is similar to triangle CEY, we will conclude that CE over CY in triangle CEY is equal to CD over CM in triangle CDM. So CE over CY. What is the value of CY? The value of CY, you can see here that CY is the radius of the middle circle, that is to say it equals to 2 units. So CY equals to 2 units and it equals to CD. What is the value of CD? The value of CD, you can see from the drawing, CD equals to 2 minus R and R equals to 1, so CD equals to 2 minus 1, that is to say it equals to 1. So CD equals to 1 unit and CM equals to R plus 2. You can see from here that CM equals to R plus 2 and R equals to 1. So R plus 2 is 1 plus 2, that is to say CM equals to 3. CM equals to 3. So in total we got that CE over 2 equals to 1 over 3. Here we multiply the equation number 3 by 2 and we got that the value of CE is 2/3. We found out that the value of CE is 2/3, and then DE equals to CD minus CE. Again, DE equals to CD minus DE. DE equals to CD minus CE. CD minus CE equals to DE. Okay, DE equals to CD minus DE, and CD equals to 1, and C equals to 2/3. So in total we got that DE equals to 1 minus 2/3. 1 minus 2/3 is third. So we found out that DE equals to third. And OE equals to, and OE is OD plus DE. OE equals to OD plus DE. You can see here that OE, this line segment OE equals to OD plus DE. Okay, OE equals to OD plus DE, and OD equals to 1, it is the radius of the small circle, and we have already found out that D equals to third, so in total we got that OE equals to 1 plus third. 1 plus third is 4/3. We found out that OE equals to 4/3 units, and then we focus with connected points O and M together by a straight line, and we actually proved, first of all, that in the triangle OBE, this triangle is a right triangle. Why this triangle is a right triangle? Because we know that AB is parallel to PQ. Therefore, the sum of those two one-sided angles must be equal to 180 degrees. Okay, we have rule number 3, that the sum of one-sided angles between parallel lines equal to 180 degrees, equals to 180 degrees, and we know that AB is parallel to PQ. AB is parallel to PQ, and those two angles are located between those two parallel lines AB and PQ, and therefore the sum of them are equal to 180 degrees. So this angle that is 90 degrees plus angle OEB must be equal to 180 degrees. Okay, angle, according to rule number 3, the angle that equals to 90 degrees plus angle OEB must be equal to 180 degrees because of the fact that those two angles are one-sided angles, and the sum of two one-sided angles that are located between parallel lines are equal to 180 degrees, and angle that equals to 90 degrees plus angle OEB are located between the parallel lines AB and PQ. Therefore, the sum of them is 180 degrees, we subtracted 90 degrees from this equality, and we got that the size of angle OEB is 90 degrees. So this angle is a right angle, and because of the fact that this angle is a right angle, therefore triangle OEB is a right triangle. So we found out that triangle OEB is a right triangle, so I copied the right triangle again in the new page. So we have the right triangle OEB. So the right triangle OEB is a right triangle. This triangle OEB is a right triangle. So on this right triangle, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, OB square equals to EB square plus OE square. According to the Pythagoras theorem, in the right triangle, triangle OEB, OB square equals to OE square plus EB square. OB equals to 4, so OB square equals to 16. OE equals to 4 over 3, so OE square will be equal to 4 over 3 square plus EB square. So 16 equals to 4 over 3 square is 16 over 9 plus EB square. So here we subtracted 16 over 9 from this equation, equation number 4, and we got that 16 minus 16 over 9 equals to EB square. Then we multiplied 16 by 9, and then we divided by 9 in order to have a common factor with 16 over 9. And we got the 16 times 9 minus 16 over 9 equals to EB square. And 16 times 9 minus 16 is 16 times 8. So we got that 16 times 8 over 9 equals to EB square. We took a root out of equation number 4, and we got that EB equals to the square root of 16 times 8 over 9, and 16 equals to 2 times 8, so we substituted 16 by 2 times 8. So EB equals to the square root of 2 times 8 over 9. The square root of 8 times 8 is 8, and the square root of 9 is 3, so in total we got that EB equals to 8 over 3 times square root of 2 units. Okay, EB equals to 8 over 3 times square root of 2 units. Then we actually proved that those two green right triangles can go into each other. I copied again those two right triangles, and we proved that those two right triangles can go into each other. Why they can go into each other? Because of the fact that OA equals to OB equals to 4 units. It is the radiuses, they are the radiuses of the semicircle. They are equal to each other. OB equals to OA equals to 4. And OE is a common side, it belongs to both triangles, so OE equals to OE is a common side. Therefore we proved that those two right triangles can go into each other according to the rule that if you have if the hypotenuse and the perpendicular of one right triangle can go into the hypotenuse and the perpendicular of another right triangle, then the two right triangles can go into each other. And we proved that the hypotenuse and the perpendicular of this right triangle can go into the hypotenuse and the perpendicular on this right triangle. Therefore we proved that those two right triangles can go into each other. And because of the fact that those two right triangles can go into each other, we will conclude that AE equals to EB. Okay? AE equals to EB according to the rule that corresponding sides in congruent triangles are equal to each other. That is to say, AE equals to EB. And what is the value of AB? You can see from the drawing that the value of AB equals to AE plus EB. AB equals to AE plus EB. But we already know that AE equals to EB, so we can substitute AE by EB, and we will get that AB equals to EB plus EB, that is to say AB equals to 2 times EB. And we already found out that EB equals to 8 over 3 times square root of 2 units. So AB will be equal 2 times EB, that is 8 over 3 times square root of 2 units. 2 times 8 is 16, so in total we found out that AB equals to either 16 over 3 times square root of 2 units, or in terms of numbers, AB equals to 7.54 units. I'm repeating again, the size of chord AB, it is equal either to 16 over 3 times square root of 2 units, or in terms of numbers, the size of this chord AB equals to 7.54 units. Okay, thank you very much.